So there will be other advantageous principle that could be, advanced principle that could be considered in here. Say, for an example, surface acoustic waves, a very sensitive method to detect virtually anything. The principle is that on a resonant surface, you send waves, and this wave will deviate from their standard response if you excite or you modify something. What you modify could be anything: humidity, temperature, pressure, whatever you modify, you could detect with a according, it's called delay line, according design of that delay line. So could be done. The point is just, I mean, there are lots of research on that. The point is that none goes for that specific application. It's true, if you come and say, I need 750 degrees, I will say, oh, no, I can't do that. It's too much 750. It's always a trade-off process in here.
What's the current state of the art for temperature for solid surface acoustic devices?
Would be crystal 750 degrees tops, probably. Now, depends on what you want to measure. If you have the delay line made from a polymer, it's the temperature of the polymer. Right? But if you have some other sensitive material, it will go fast. All right. Electrostatic sensor for gas path debris detection, for an example. I mean, it's another option. It's not there. It's not built. It's not shown. This is the sensor. Take it. Microwave, eddy current. Eddy currents are used for outside tests. So the pen and you check if it's any crack, whatever. But eddy current as a principle could be implemented, embedded somewhere, if it's a critical surface, and have online real-time detection of defects or cracks or flaws. So Doppler velocity interferometers for vibration, with no contact vibration, very good for that purpose. You don't have to hang anything, it just goes in there. Not very accurate, but good enough for many type of applications. So there is some technologies that could be watched for that purpose. Now, regarding the wireless, I'm already exceeding the time significantly. I just want to go with that. Wi-Fi is not reliable sufficient at this time, because in aerospace, anything we discuss in aerospace has to be reliability of 7 nines. Right? So that means 99.59. Or Wi-Fi is not doing that at this time. Wi-Fi, RF, Bluetooth, Zigbee, whatever technology for wireless is not accurate enough. We lose bits, so that is not acceptable. For control, there is no way that this technology will be implemented in probably in my lifetime. Unless something outstandingly happens. I don't live long, this is the point. So, basically, if we have such sensors, it would be definitely a good point. The issue would be, how do you power them? Because you come with 2 wires, what is the point to have a wireless? You still have to wire it, right, for power. So for that, one needs to scavenge energies from somewhere to get whatever, temperature, light. There are sources. There are attempts to do that. Probably you saw on the road this indicator for speed to tell you if it, and they are supplied from the light. Yeah, but the same thing. They have limited life. They are bulky. The issue is that when can we produce this type of sensors reliable enough to operate in aerospace? So I think this is what is going to be. Controls will stay on wire, and probably condition monitoring, if those sensors are implemented, will go Wi-Fi.
And as was mentioned yesterday,
exactly.
There's always a threat of malicious.
Right. Yes. I mean that usually. I mean, what will happen? Condition monitoring will progress probably faster because of that. And at one point, when we gain the critical mass, we'll push into the controls, and we'll make an advance in controls. It's normal somehow. You don't go in the critical thing, and you don't bet your house, right, when you go to the casino. Just what you have in the water, more or less. Whatever. Packaging is just an example of how people try to do the detection of temperature gradient on a plate. I mean, this is a good idea to embed them, but this goes only for test, goes only for the one blade, goes only in the lab, would not go in the field, right?
It's actually a MEMS device?
Yeah, yes.
Okay.
It's a temperature-based. So, say for example, we have means to measure temperature, pyrometric. You know the gun, you set it on the direction, check the temperature of color. But the variation, the accuracy might be, it's always less than 30, more than 30 degrees. This is the minimum delta T. Or in 30 degrees, if you exceed by 30 degrees temperature in a burner, the light probably decays to half or so. So that accuracy is not sufficient to move towards this technology for measurement. We need still accurate measurement within 2 degrees or so. Issues for optical detection or the diodes is the fact that through optical in burners might contaminate, might cover in fumes, and basically alter the measurement, the indications, right? Talking about acoustic noise, temperature could be measured acoustically. So how it goes that if I have a resonance tube and I produce a frequency that will hit that tube, a resonance will build up in the acoustic tube and will maintain at the same frequency. This frequency would not be dependent on the pressure but only on temperature. So if temperature changes, the frequency will slightly alter. If I have means to measure that, it's fine. In a gas turbine engine, unfortunately, the dB level is 160, 140 dBs. It would be very hard to measure modification in the frequency in a resonant tube to be 65, 70 dBs probably tops. So unless we select a certain frequency band in which we don't have noise produced by the engine. But to my knowledge, noise is about everywhere here. There's no bandwidth in the
very broadband. Internally, it's very broadband.
Right, yeah, exactly, very broadband.
Flames produce everything.
So, pressure. Now, this is 2008. Things has changed for sure in here. But again, maximum level we have is 750. What we need for activity in LED control would be 3-bar operation pressure plus minus 0.1% accuracy, which is demanding. Minus 60 plus 50 is 65 degrees temperature. For the inlet is the most, I should say, gives the most reasonable range of temperature. We move from here, we have a little bit of a problem.
Question. Now, how do you get those numbers to, like, for example, the spectrum accuracy?
Well, it's a very good point. We had this session in 12 people, 12 angry people in Athens, and we sat at the same table for probably 16 hours, and we just squeezed these numbers. Everybody called his, information sources, and we figured out this is what we have. So why I'm going through that? This will be at the end of. Let me just go in there for illustration, and still a long talk. You have everything in a tabular form. So the requirements are environment requirements specific. This is the environment condition, temperature and pressure eventually. Requirements, which is resolution, bandwidth, range, accuracy, whatever we could extract at that point. We try to fill in every box. That is the issue here. Some of them we are fully aware that what we have in here is not necessarily the reality. But this is what we felt at the same time was our best guess at the time. Right? The application is listed in here. The technology that would do it, we have a TRL level, as we thought at the time, TRL 1, 2, 3 is just early stage. And challenges, eventually, what found as challenges. And we also included a year to achieve TRL 6, which would be the time when technology would take off. Right? Recall from Sanjay, 4 to 6 is critical. Basically, about any technology dies in there. So we have this table, which is quite significant as dimension here by grid, based on the physical quantities to be detected. So now what I have in here is just discussion point by point of that table, right? So I don't think it's, I mean, you could go through that. It's not a very fast time. It's not something remarkable that has to be discussed on that. What I wanted to bring up, this is the next slide, is the fact that you see all these resolutions are not mundane. They are not 2.5%. They are quite significant, and you attach that with specific, let's say, pressure sensor for detection at 35 kilopascal. That is fine. Dynamic, we can, it's 35 kilopascal, sorry, 40 kilohertz. It's fine for piezo. But if I have to measure static pressure, I can't do that, honestly. Static pressure, static pressure, dynamic pressure, but not in dynamic way. Okay? It's not relative pressure, absolute pressure. That would be hard.
Not impossible.
Not impossible yet, but look at 40 kilohertz, look at the resolution 0.2%. So that would be okay. We have to think. You can't just call and say I could do it, no problem. You have to think. There are challenges indeed. Some of them, they are less demanding. So, for example, 1 hertz bandwidth. But what we have in here is 500 to 700 centigrade. So it's another challenge, right? What is interesting in here, again, that would be okay, sensor flow or separation. That would be in the inlet. So the temperature is reasonable. Inlet, everything is fine. Thermoacoustic instabilities in the burner, that is hard. That is very hard. I know that on the static, on the energy turbine, Bosch built a stability control tool that would detect basically instabilities and modify the flow of fuel, of the injection of fuel, to secure the stability of the burning. Right? So this is not difficult. 1 kilohertz probably is not difficult. 10 kilopascal is not difficult, but this is difficult. 1,700, right? Vibration sensors. Now, ADXL, they have a filter. They stop them to operate at 1,000 hertz, 1 kilohertz. You could push them to 2 kilohertz, but 40 kilohertz is not easy. So we talk about piezo again, or a completely different design. So we should, okay. A new lens could be designed, a new accelerometer could be the air bubble accelerometer. It's not so accurate to be, considered this range in here. Selectivity is considered 3% as reasonable. Combustion emission, so that is probably the diodes or laser-induced spectroscopy. Heat clearance would be radio frequency probably. This is what we assume at that time. Again, the input was from the participating members, and we had more or less, we had many industries in there. We had also G and Pratt and General Electric. Torque, that is, there are many ways to do torque, and you see the requirement is not so harsh. That would be achievable, and this time we have sensors.
Any turboshaft engines include torque sensors.
So they are there.
And they are commercially available. Durability of them is sometimes a problem.
Torquetronics.
Yeah.
Yes.
But it's a standard product.
Position, arrival time. So that would be also radio frequency or magnetic or Hall or whatever is ferromagnetic things. Bandwidth, this will be the issue, 40, 50 kilohertz. That is not easy again to achieve.